once those are posted to our website. For this webinar today, everyone is on mute, so please submit your questions via the question function so please submit your questions via the question function, and we will cover as many questions as we're able to during the Q&A at the end of the presentations. You can see on the slide that you should be able to see on your screens now. You can see the question box highlighted, so please enter your questions in there, and we'll sort through them for the Q&A period. Also, since we have multiple speakers today, please indicate who your question is for when submitting your questions. Now, our webinars are part of a series, so please check back to our website for future webinar topics, as we'll be hosting them monthly. And also, I want to encourage everybody to sign up for a Fuel Cell Technology Office newsletter that we send out monthly. You can sign up for that on our website. Now, I'm going to turn it over to Blake Marshall. Blake is a technology manager in the Advanced Manufacturing Office. Blake.
Thank you, Amit. So yes, I am a technology manager in the Advanced Manufacturing Office, as Amit mentioned. Not a terribly descriptive title, but generally my role here is to manage a research portfolio of public-private partnerships, specifically additive manufacturing technologies. And I manage the manufacturing demonstration facility that is run out of Oak Ridge National Labs. I'm also very delighted to introduce two industry partners that are going to be presenting today as well. So we're getting a diversity of perspectives here. First, I'd like to welcome Bradley Wright. Brad is a senior mechanical engineer for Eaton Corporation. He focuses on research and development of roots-based waste heat recovery systems and air movement devices. He's also the lead of Department Energy's Roots Air Management System with Integrated Its Expander program. A support engineer for the Heavy Duty Roots Expander Heat Energy Recovery Program. And he has a combined 7 years of experience in R&D with Eaton and also Air Force Research Laboratory, as well as 5 years experience with quality at Toyota Motor Company. I'd also like to introduce Benjamin Lunt. Benjamin has been with as a senior mechanical engineer with Nuvera Fuel Cells for 7 years. He's responsible for research and development of fuel cell stack and subsystem technology. In this role, he both documents and controls existing products, as well as work on developing new designs and equipment for R&D. Okay, so without any further ado, I will give a brief outline of the presentation here. I'm going to start out very quickly just by giving a very high-level overview of the sort of technologies that we're referring to when we talk about additive manufacturing. Then I'll move on to a few of the reasons why we might be interested in additive manufacturing, specifically as it relates to fuel cell technologies, and trying to dig into some of the capabilities that may be of particular interest to fuel cells. I'll then move on to describe some of the DOE perspectives, what we're doing in the additive space, and why that may matter to you. And then, of course, we will move on to our industry perspectives. Brad and Ben will give their experiences with additive manufacturing technologies, and then, of course, we'll round it out with a question and answer period. So please submit your questions via the questions function in GoToWebinar, and we will wrap up with a good discussion. So, what is additive manufacturing? You'd think it's a simple answer to that question, but it's actually it's a little nuanced here. The first thing I'd like to point out is that when we talk about additive manufacturing, and in the context of this webinar, we're not talking about a single technology. We're talking about a whole wide range of technologies, so a whole set of different technologies, and generally emerging technologies, so in various stages of development, but also with plenty of commercially available products. And the second point I'd like to make is that when we're describing additive manufacturing today, the essence of what we mean is that we are fabricating parts with a layer-by-layer technique, and you're only placing material where you want to, essentially. And then that's all done in the digital realm. Basically, you go from a CAD file to a part, more or less directly. Just to illustrate how a few of these different technologies, it's a whole wide range as we mentioned. But I'm going to walk through just a couple process examples. And a couple animations, which are a little cheesy, but they help get the point across here. But this is a fused deposition modeling example. So basically, again, we have a polymer feed coming in and, to the wire to a tool head, which then applies heat and then melts this polymer in a layer by layer manner. And here's an example. You can see this part. This part was actually grown using this process. And you can see, if you could zoom in here, you'd see all these various layers building up to this final part. And this is that machine zoomed out a little bit. And this is an example part that you might get out of such a process. Just note the internal passageways in here, and someone designed this part exactly like this in a CAD program. Another example would be directed energy deposition. So this is, imagine the same thing, but just with a metal wire and an electron beam for heat, to provide your energy source rather than just a heated nozzle. And it just builds, again, layer by layer. And here you can see these various layers actually if you zoom in, because this is a very large-scale machine in this case. And here's an example of that. So this is the Siaki process, and this is a very large build volume. I think this one would be 19 feet in length and by about 4 feet in this dimension. The last example process I'll run through is important for this discussion, because I think we'll discuss a few parts later on that actually are being used in fuel cells now. Is powder bed fusion, and the basic process here is you apply powder over in front of an electron beam, which then just melts the powder wherever you need a part, and then the part sort of grows downward as you grow the part. Here's just an example of an electron beam hitting that powder bed. This is what a machine might look like, and these are two examples of parts that were built during this process. I will note it's not always, the energy sources can vary, so lasers and electron beams are what you tend to see with these processes. So those were the first three that we just discussed: powder bed fusion, directed energy deposition, and material extrusion. This is just illustrating the point that there are actually a whole wide range of technologies that we're talking about here. We won't even really go into details on any of these. But there are also, a lot of different processes and a lot of different materials. So we're by no means going to cover all of these. We're just barely scratching the surface. But there are a wide range of technologies to explore that may or may not have good application in fuel cells. So I'd like to move from that to the more general aspects of additive manufacturing that can really be important, that are unique capabilities, we think, to the technologies. So these are, we're basically focusing on the capabilities and the benefits of additive as opposed to the technical challenges in this webinar. The reasons why additive are so beneficial is that you can control the topology, the design of the part is wide open in a sense. There are limitations, but it's much less manufacturing limitation than some other processes that you need to have a billet of a certain size and the machining capabilities, etc. So it enables entirely new designs that weren't possible before. Additive can also shorten lead times dramatically and can lead to very fast prototyping, and we'll show some examples of this. It can also make parts that are just higher performance than a similar part made in another manufacturing technique. There are also other extended benefits in the supply chain and inventory benefits. If you can imagine, rather than having to warehouse parts, you keep a hard drive of parts. It's obviously a very different situation. And you can also, there are cases where you'd move from a many-tiered supply chain system to one where you're making all of the parts that would have been spread out in a supply chain. So there can be supply chain disruptions and things like this that maybe could be avoided. That's not really the scope of this webinar necessarily, but it's worth noting. And in general, additive is good for certain parts. It's really not, it's not going to be cost effective for a lot of different things. I think the point of this discussion is trying to understand the sort of niches where additive could really make a benefit now. And those places are good when you really want new designs, when you really feel limited on what you can make. When you want really complex parts, complexity is essentially free with additive. It doesn't take any more effort to make complex parts. Small runs, customized components, and you can also get some advantages when you take a whole complicated assembly that's labor intensive and costly and reduce it into one build, one part. Here's an example of an entirely new design. GE had a very complicated fuel nozzle that was made of 20 different parts on previous engines, and it was very time-consuming to assemble, essentially, and very costly. So they redesigned it. Here's the part. It's all printed. Some of these surfaces were machined after the fact, but it's all one part. So it's a new design, and here's a direct quote from the lead engineer. I need very complex shapes. I need shapes that a machine tool simply, just cannot generate. So whole new designs are possible. It can also speed, shorten lead time and speed prototyping. Here is a sort of toy example, but I'm only speaking to it because I have some first-hand knowledge. We got a printer here in the office to try to help illustrate, the capability when we're out and about. And I just pull up the computer, put this together, and the whole process was 2.5 hours. So of course this doesn't have any real-world application, but if you imagine coming up with a new design and a new prototype in your R&D shop, you can see how a capability like this could be pretty useful. And here's a real-world industry example. Full disclosure: this is a producer of additive manufacturing equipment, but they claim reduced cost by 90% and dramatic decrease in lead time. And this is for a metal additive part as well. High performance parts are also a core to the capability, we believe. I won't go into details on this very sort of rigorous energy study. I'll just kind of walk through some of the high-level points. We compared conventional machining for an existing real part to an additive manufacturing approach that could produce the part and then with some optimization. And we saw that there was a dramatic energy savings with this, and this is an actual part, just to keep in mind. A lot of those came from the fact that the part was lighter, 0.38 kilograms as opposed to 1.09, and this was being flown around in a jet, so that's where the use phase savings were pretty evident. But also you'll see things like the manufacturing energy was dramatically lower as well. So this is a unique case. Every application needs to be weighed, but in this case we saw a lot of, a much higher performance part due to lightweighting, and these are just some of the studies for that. I'm just going to go through really quickly and give a few more random examples of some of the things that additive, just to maybe spark some thoughts that additive can be useful for, maybe in the context of a fuel cell. This just looks like a hand, but you'll notice that, and it is it's a robotic hand assembly, but you notice that additive is able to make this fine mesh, which can be really good for, I can imagine, increasing surface area and also just decreasing weight. But you'll also notice if you look in here, there seems to be something here. And I can't really show this very well in pictures, but this hand has an integrated pneumatic channels with actuator pins that actually move these fingers. So there's a whole complicated network of channels that are printed right in here with no extra process steps or anything like that. And something like that wouldn't be possible at all. It'd be another process. Here's another example, just a toy, but it's a small ball. But when you pick it up, you notice that it's not empty. There are other things rattling around inside of it. And if you really zoom in, you can see ball after ball after ball printed totally independently of one another. That's just a powder bed process, and it just they kind of roll around inside of each other in their hand. So pretty much, if you can think it up, additive may be able to print it up. Here's an example of a part that was designed by a student, and it looks to be a solid part. It was for a robotics competition, a national robotics competition called FIRST. It appears to be a solid part, but if you stop that build halfway through, which we did here, you'll see that even in this simple case, this part is building in airspaces all in the inside, the interior of this part. So this wouldn't, of course, be possible with a casting or something, and not unless it's a very advanced casting technique, which would be very costly to do. This is sort of this can be a de facto sort of printing technique with additive manufacturing, which could be beneficial for saving weight. This last example is a bracket that General Electric was interested in looking at, and they did something really unique. They rather than working too hard, I mean, they took this part and they tried a new model, and they basically on their website just had a design competition, and they invited anyone to come up with an optimization for this part that they might be able to print. And this is just one example of one of those parts, but there were hundreds of these different part optimizations coming in with all kinds of different features. The point being just that you can really come up with new ways to approach design with additive manufacturing in some cases. I'll just give you a brief overview of why the Department of Energy is involved here, and why we're very excited to talk to you today. Just to give you some context of where I am, in the Advanced Manufacturing Office relates to the fuel cells. So we are all we're in the Energy Efficiency Renewable Energy Office of DOE. And the advanced manufacturing technologies that we focus on are cross-cutting and broadly applicable. So in this case, additive manufacturing we see as it could have application in a variety of different contexts, but what we're really interested today is how might additive manufacturing benefit fuel cells technologies. So here's just that, just same thing in writing here. So we define additive manufacturing as a key cross-cutting innovation technology. So that's a little bit of what, we're focusing on additive manufacturing, and this is a slide just to quickly demonstrate how we do that. AMO's investments in additive manufacturing are through shared R&D facilities. So basically, this, which is symbolized by this box here, so it's essentially infrastructural. We set up a shared user facility program where OEMs, so in this case additive manufacturing equipment suppliers, can put their equipment in. And then by doing so, they have access to the staff expertise and maybe a variety of other capabilities. But the output for them is improving their process, for one, research and development, but also potentially industry partners that might use their technology in the future. The other way through the MDF is perhaps more relevant here, is that other folks come to the facility looking to try out the new equipment. So you have a new design for whether it's a flow field or whatever it may be. You have the opportunity to come and access this equipment at a lower cost than you otherwise would, and hopefully develop, by going to the facility, develop all the data you would need to make a business case to understand what your risks might be, what your costs might be, and all these factors of production that you could get with, at a lower cost, and ultimately that leads to innovative products, obviously. So these are some of the reasons why we would choose an R&D facility approach as opposed to funding individual projects, for instance. And you can read them here. I won't go through all of these, but ultimately this model has we hope, a positive impact on U.S. competitiveness. We have 2 R&D facilities that are focused on additive manufacturing. In a sense, America Makes is much larger than DOE. It's been mentioned in 2 State of the Union addresses, but we are a partner in America Makes, which is the pilot National Innovation Institute. But we also, our office focuses on the manufacturing demonstration facility in the MDF in Oak Ridge National Lab, which is funded mostly out of this office. So if you have any questions, please feel free to follow up with me. As I mentioned, I'm the manager of the projects that are managed out of the Oak Ridge National Labs MDF. And Kelly Visconti, who is not presenting today, looks over the America Makes work. So please feel free to follow up with either Kelly or I if you have any questions offline. Thank you. So without any further ado, I'm going to pass the microphone over to Brad Wright.
Okay, so hello, let me introduce myself again. My name is Benjamin Lunt. I'm a senior mechanical engineer at Nuvera Fuel Cells. I did have, in my R&D experiences, a lot of opportunity to use additive machining or additive manufacturing, and I will be presenting a case study in that coming up. Next slide, please. So the abstract of this is a review of a development project using direct metal laser sintering. Basically, what I've done here is developed the next generation anode recirculation ejector. I used additive manufacturing to prototype these and test these for use in fuel cell systems, PEM fuel cells. This process, it was selected for its short lead time, low cost relative to machining or molding to achieve the designs that I wanted to test. Next slide, please. The outline here, I'm sorry. Okay, here we are. The outline is, I'm just going to look at some of the things that we've been already speaking about today: complex shapes, design innovations, weight reduction, multiple design variations in a single build, and product development, component integration. Next slide. So this is an example of one of the parts that I used as part of this development study. Direct metal laser sintering was used to create the complex geometry that you're seeing here. The photos don't always necessarily show you how complicated this part is, but you can see that there's intricate nozzle nested on the inside of this part, and then there are other small gas passageways to allow for the pressurization of a valve, the valve which is used to actually control the anode flow. The ejector, nozzle, throat, and diffuser were all built in one part. Previous machine parts that were similar to this were machined in 2 or more pieces and then welded together, and that was necessary to get the detail on these parts, and then they would have to be assembled, aligned. The machining would have to be very precise to get the nozzle alignment where it needed to be. So it got very expensive. The tolerances were very tight, and you can see the example of the machine part next to the prototype part, that there's an obvious difference in mass. Obviously, because of machining, it just costs more money to machine away extra material that doesn't necessarily need to be machined away. But in additive manufacturing, you can just put the material where you want it. So I was able to get a lighter weight part, and I got the material where I needed it, and I was able to move forward with my testing. Another benefit that I got from this is the flexibility of being able to add in certain design features to make this a twist lock part instead of having to press the pieces together and then fasten them with hardware, or slip fit and fasten with hardware. So the tolerances that were required were actually a lot lower, and the part was easier to assemble just with a simple hand twist. Next slide, please. I'm going to talk about that a little bit more here. So if you look at the photo on the bottom, you can see the twist lock feature. There's actually a hook, and then there's a feature, a boss on the other part. So the boss would go into this groove and then simply twist lock the part together. There's actually a spring inside, a valve mechanism, that holds tension on the part so that it doesn't come apart. So this eliminated the need for hardware. It made these parts very quick to assemble, and with the tolerances that were available from the additive manufacturing, we were able to build these parts and twist them together quite easily. This complete assembly was made from 3 pieces total, so you could see the 2 twist lock, the body of the valve, and the actual ejector portion. In the center of the part, there's actually a piston that moves back and forth, and the piston is controlled by anode pressure. So when the anode pressurizes to a certain point, it pushes against the spring and starts to close the valve, so it actually controls the flow of the reactant into the ejector. But this is basically, from a manufacturing standpoint, the minimum number of pieces that you could possibly put was 3. So it was actually possible to make this in 3 pieces, and it's a twist lock valve assembly with an ejector. This would have been a lot more complicated to do with machining, and, well, it wouldn't have been impossible, but it probably would have been a little bit more expensive to do so. One of the advantages here is able to build a prototype. I'm not committed to that. I'm not committed to tooling. I'm not committed to complicated programming. I mean, there is still programming involved, but it's not multiple programs like CNC, EDM, wire feed. I just can do this with a single process. For the long term, I'm looking at metal injection molding as possibly an alternative to the additive manufacturing, but that would be for much higher volume because of the tooling charges or the tooling costs associated with that. So for the near term, even for small and medium volumes, I'm looking at DMLS as a solution for this part in short production. Next slide, please. Here's an example of basically some learning that I had with getting more familiar with the DMLS process. The first part that I built on the right-hand side, you can see that there's 4 small holes but very solid body. I had originally designed that to be hollow on the inside. Unfortunately, there was some issue of getting the media that's actually used, the powder used, out of those small holes. So the manufacturer I was working with was concerned, and well, we decided to make it a solid body. Making it a solid body was pretty heavy, but after learning that and getting a better understanding of the process, I was able to change the design to the one you see on the left, which is simply 4 spokes rather than small holes in a hollow body. I basically hollowed out as much as I could and left the 4 spokes to hold the center, and that was possible to build, and I could get the powder media out after the fact. So this is a good example of weight reduction that can be done even from my first experience with using this process to my later learning a little bit more about it. Next slide. Another advantage I had with using this technique is I was able to basically build multiple parts in a single build, and as long as everything can fit on the bed of the machine, so talking to your manufacturer, you get an idea. I believe the machine I used here was 250 millimeters by 250 millimeters. So what I wanted to do is take advantage of as much of that surface area as I could, and I built as many parts as I could in one build. Having done this, I was able to kind of get a test matrix together for different size ejectors that I wanted to use. I wanted to come up with a family of parts that could be used for my entire projected power range for my fuel cell systems, which is about 10 kilowatts to 90 kilowatts. In this testing, I chose 3. 3 points defines a curve, and then I was able to kind of look at the 3 different sizes, see what kind of ranges they were optimized for, and then design my family of products for my final designs. Next slide, please. Here I'm showing a project that I was looking at as far as further integration of balance of plant components. On the left-hand side, what I did is I included a boss that I would be able to post-machine to be able to accept a solenoid valve, and the solenoid valve would be my hydrogen inlet valve. This is an example of some of the, I guess, thinking outside of the box things that you might be able to do, and when you're working with a process like this, it becomes very, the world opens up a little bit, so you can really take a look at integrating more parts or more components. This was a particular one that I have not tested yet, but I did come up with the geometry, and it is definitely possible. However, valve selection being what it is, I haven't really committed to using the valve that I was planning on using here for some reasons, but this is an example of one case where you can take a look at other components and integrate, more deeply integrate your system into fewer pieces total. Next slide. So here's my conclusion slide. Basically, direct metal laser sintering was used to achieve an optimized ejector design. With several iterations, I was able to look at a bunch of different design options, test a few different ones, and this was all done building only a handful of builds on the machine. And the final designs are now optimized, and I have a high level of confidence. And if I was ready to move forward with higher quantities, I could be much more confident that I would be investing in tooling that would be creating a part that would work. And that's the conclusion of my presentation.
Great, thank you, Ben.
Thank you.
Okay, I guess we'll give try to give Brad one more. Let's see if Brad can come on the line. Brad, are you able to speak?
Yes. Can you hear me now?
Yes, we can. Great.
Okay, good.
Just give me a few seconds to get back to your presentation, and I'll let you take it away. Okay. All right.
Okay, let's wait for the beginning to show up on my computer. It seems to be acting a little slow.
Oh, is there a delay?
Yeah. Yep. Okay, my name is Brad Wright, and I work for Eaton Corporation. I was going to give you my perspectives on what we've been using additive manufacturing for, and specifically speaking to the facility that I work in. We do quite a few different product development situations. So I'm going to speak directly to Roots air movement devices and some of our waste heat recovery systems. If you would, please go to the next slide. So a little more in depth on how we use additive manufacturing. We're going, and we have a Dimension SST plastic printer. So we do quite a few FDM models. We also source out some of our metal substrate models to different vendors, and a couple of different rapid prototyping techniques are used. If you would go to the next slide, please. Okay, so I'd like to cover what we use our plastic substrates for, our internal capabilities, some of the applications that we've applied to the parts that come out of this machine. We also do some testing and have in the past done some low volume manufacturing with the plastic substrate. With the metal substrate, we've started doing several prototype builds. We're using DMLS technology and also rapid cast. And then I'll touch on some of the value propositions, at least according to the scope of research and development, on what kind of considerations we take into costing and the method and the substrate used for each of the parts. Next slide, please. Next slide. Oh, there it goes. So here in my facility, we have a Dimension SST. It is an FDM or a fused deposition modeling machine. It's quite small. It's probably the size of a refrigerator. You can see it down here. It's the second to the left. Basically, what this does is it takes an ABS filament wire, and it heats it to near melting temperature, and then a nozzle will lay this sticky filament wire and place it in such that it forms a plastic part. There's also a sugar-based support structure that's laid down as well, and that helps conform the model to specific dimensions and helps cover any of the gaps that are created when the model is being built up. So you can see on the far right, we have the finished plastic part. That part is probably 5 inches by 2 inches and 5 inches tall. And that part would take approximately 3 to 4 hours to print and 3 to 4 hours to remove the soluble support structure. So about 8 hours, we go from design to actually having the part in hand ready to use. Next slide, please. So the applications is really quite endless, but what we use them for is design models. So I can print up a unit with completely different geometries, or I can take existing parts and I can build new parts for them. I can print them quickly, and within the course of hours or a day or two, then I have parts in my hand that I can actually analyze for fit and for function. Does it look right? Are my timing ports correct? And although that can be done in a CAD model on the screen, it's also much value added when I can have the part in my hand and make physical models and take them and discuss them with other people. That brings us to kind of the demonstration and customer models. So we can print out full units or almost entire system components, and we can share them with customers. We can show how they mount to test fixtures. We can mount them directly in application and show a lot more than we could with just a 3D picture. The most value that we seem to be getting from this particular technology is that we can make test components. If we work within the material limits, I can test components almost the same day. So if we could go to the next slide, please. So this can be really ideal in quite a few situations. Number one is if I'm trying to set up a test, and a lot of the components that we have are 1 or 2 off prototype components. So some of the bolt-ons, add-ons, or adapters don't exist. So we have an in-house machine shop, but I have to go and design it. I have to build a print. I have to modify the GD&T and then submit it. And then the turnaround ends up being a week or two to get a billet part. If I can go back to my desk and design a part on my system, hit print, and have that adapter or that unit that I need in several hours, and I can get the test run for the same day. Also, if I, like I mentioned before, if I work within the material constraints, I can use this for the actual test part itself. So I can, for instance, if we look in the pictures for that labeled with B, this is actually controlling the airflow into the device. So I can create multiple geometries and do an entire test matrix with just the printed parts. So talking to the limitations, at least for this particular material, again, this is a ABS material. So we've tested up to 2.3 bar with a 4mm wall thickness and have pretty good success with that. They will accept thread inserts. They have reasonable clamping and compression loads. So, for instance, example C, you can see that there's a hose clamp on that. We have fasteners that go through the part, and these will hold up reasonably well. And if I only need to do 1, 2, or maybe 3 tests, then these work quite well. So we do have a process that once these come out of the printer, they need to go to the water-soluble portion where the support structure is removed. And then once they come out of that, they're dried, and we paint them with a very, very thin solvent. So these models tend to be somewhat porous, and we think if we coat them with the solvent, they become less porous and a little more structurally sound. If they do have a temperature limit. We found that the material that we're using has a very strict 115 degrees C temperature limit. If we exceed that, we see cracking, brittleness, and blistering. You can see that in picture D. This particular example experienced all of those. And it doesn't take much over 115 to kind of create this. But again, if we work within the material constraints, it's extremely useful and provides very, very quick and cost-efficient turnaround. Next slide, please. So kind of pushing the boundaries of that a little bit, we've actually done some customer engineering samples and low-volume manufacturing with the plastic components. So to the right, we see that was the customer engineering samples. We built approximately 20 of those. And the black portion of that unit contained the electronics. And we were able to print that unit and assemble them the same day. We can do any part revisions. If I print a part and I go to assemble it and I see that something needs to be changed or could fit better, then I can immediately just go change it on the model, print another one, and have it again, sometimes the same day. You do have some durability constraints. Material selection is getting more broad. There are more robust materials available if you know your primary focus. You can find a machine that will run a material that will do that appropriately. For low volume manufacturing, we've shipped almost 40 units of the part on the lower left that they're printed on demand. It's a low volume sales unit, but it allows us not to have any manufacturing or warehousing needed for this part. Whenever a part is ordered, we print it out and we ship it. It only takes about 2 days to make this part. And the actual cost is less than what we would have for a traditional manufacturing this part. Next slide, please. So moving on to the direct metal laser sintering. So some of our prototypes, actually most of them need to be aluminum or steel, and we find that with billet we have sometimes extremely long lead times on the order of 5 to 6 weeks. So we've been moving towards doing some of our prototype builds using the DMLS through some suppliers. We've been able to get both 316 stainless and aluminum 6061 T6 done using this technique. And so you can see the part on the right. It comes out looking much like a casting, so some final machining is necessary. Most suppliers quote around 5 thousandths tolerance. It's extremely quick lead time. This part was quoted at 4 to 5 weeks for a billet construction, and we were able to get this part in 2 days. The cost is somewhat comparable. Also, there's another method that we've utilized for producing the same part is a rapid casting. So the supplier will receive the CAD model from us. They will create an SLS lost wax disposable pattern, and then they will, using somewhat similar to traditional casting methods, but they produce the part from the lost wax 3D part. And turnaround of that is actually fairly similar to billet, but also very good quality. Next. So we've actually sectioned some 316 and 6061 components to see what the microstructures look like. So with the 316, you see that at the 500x magnification, we see some very interesting detail that you wouldn't normally see on a material like 316. And we can see the crystalline structure. We see some oxidized boundary layers that look like arcs. And we've measured a porosity of 1 to 2.5%. We expect that this material will act probably similar to cast, or maybe even a little bit better. The porosity of both the 316 and the 6061 is better than cast. So, and also, if we look down at the 6061 microstructure, we can kind of see how the formation of the microstructure and how the laser would kind of drag out the material as it's being sintered. Next slide, please. So that kind of brings us to what is the value of this technology, and how do we balance it with some of the other methods that have been used in the past? So you really need to take in to consideration your material properties and your application of your component, your part quality, your lead time, how many of these you're going to produce, does it require any tooling, and ultimately what is the part cost going to be. So if you can live with a plastic part, I can make one in as little as 8 days or as little as 8 hours. The cost is very, very manageable. If you need a metallic part and you need it very quickly, then the DMLS SLS method is very, very quick, and the cost is actually similar to billet. Rapid cast is time frame is similar to billet as well. And then, of course, if you go all the way to the longest lead time, smallest cost, then you would end up with a production standard, traditional production cast component. And there is a gray area between moving from the left to the right, but ultimately we found a lot of value in doing the DMLS technique and getting the part as quickly as possible versus waiting for a long lead time part. Okay, next slide, please. These are just some of the suppliers that we work for example. But I bet basically sums it up. If anyone has any questions, or I can hand it back over to the organizer.
Yes. Well, thank you very much, Brad and Ben. Very great presentations. Apologize, there did seem to be a bit of a delay there, but I think we got through pretty well. So we'll open up the floor to more questions. We have had several come in throughout, so here we'll just jump right into it here. And I don't know if we'll have time to get through all of them, but I'll try to bounce questions back and forth between Ben and Brad. So I have one here that sounds like I think it's for you, Brad, coming in from Will James. Most of these parts seem to be produced for lower pressure applications. If you try to produce parts for higher pressure applications, something in the 350 plus bar range, are there any safety or compliance issues based on the technique that you've considered or that need to be considered?
350 bar. Yeah, it's kind of out of the range of our typical pressure ranges that we deal with. Obviously, that would be a metallic component. We haven't done any structural testing on any of the metallic samples that we've received. I think that would be important at that pressure range to try to do some material testing and confirmations before operating at a high pressure like that.
Great. Okay, we'll have a question then for Ben. Ben, what techniques and tools are you using for quality inspection in your components? Non-destructive evaluation or other?
Yeah. Well, I have the QC department here has basically, we have used just measurements, external measurements, surface measurements to make sure that basically some of the post-processing we do, especially the machining, is inspected via profilometry and dial indicators, that sort of thing.
Great. Thank you.
One of the things that I did do with DMLS, just to add on to that a little bit, is when I first started testing these parts, I did do one test that involved hydrogen leaking because I was concerned about the porosity of the part, and the part that I actually did came out pretty good. So I have done some of that also to inspect the quality of the actual porosity of the part.
Great, thank you. Okay, so I have another question here that I think is general enough that either one could answer, and I'll start out providing an answer. The question is from Paul Dowell, and the question is, what is the thinnest wall and minimum tolerance found for metal parts? And can SS metal parts be produced? I'm assuming, well, I'm actually not entirely sure what the SS is, but I'll start out by addressing that and just preface it by saying that there are a wide range of different additive techniques for metal parts that can yield a lot of different tolerances. You have processes that are very fast that are usually powered by an electron beam, something something very large scale like the Siaki that I showed in one of my slides, or even other like an RCAM machine can make very fast parts, but they have a little bit they can't do as close tolerances, but the laser sintering parts are a little bit they're slower, but they have a higher tolerance. So just with that, would either of you want to comment on the thin wall sections and low tolerances?
Yeah, I guess I could go first. I have basically I've gone down to about 2 millimeters on the metal sintered parts that I've done. Typically the parts, I think he was referring to SS to stainless steel. I've been using the 17.4 pH, but as these techniques are getting more and more popular, more and more powders are coming out. Now there's a 316 powder that's available for doing this. But 2 millimeters is about where I'm at right now, but I think I could probably get a little thinner than that.
Yeah, that's been my experience as well. All of our experience with stainless steel has been 316. We've also done product samples of titanium, aluminum, and Inconel. There's also some other specialized alloys that are available. It kind of depends on the supplier that you're working with. The best tolerances that we've seen are on the order of about a plus or minus 5 thousandths, which I said is roughly equivalent to casting. So on one of my slides where I showed the aluminum part, we get an equivalent casting, and then final machining is necessary for any high tolerance or right, for any basically high tolerance sections.
Great, thank you. So I have another general question, and I think it could apply to either Ben or Brad. And the question is, it could be useful for there to be an analysis tool for industry and researchers to evaluate methods and costs of building their device with an additive manufacturing approach compared to a traditional approach. I guess my comment on that is asking you both Ben and Brad if there was such a tool that you did use, or if there isn't, would it be useful, and what would you like to see in such a tool?
I really think that would be something difficult to do, in the sense that we've seen wide range of part complexity versus billet, and the needle can swing to the left or to the right based on product complexity, but also based on when you do a traditional machining setup such as billet, a lot of that cost is setup cost versus how much cost is actually involved in producing the part. So with that, quantity changes the cost to production ratio.
Great, thanks. I guess this is Blake. I'll just add on that we are trying at the Department of Energy trying to understand the energy picture a little bit better. So we do have some tools that are working on understanding the energy impacts of going with an additive manufacturing process versus traditional, but that wouldn't address some of the more business side decisions that I think the question was referring to. Okay, so I have a question here for Brad. The question is, can you expand on where the soluble insert comes from? Is it made from the same print machine before the actual part run begins, or from a separate process?
The particular part that the particular machine that we use here has two cartridge inserts, one of them being the actual structure that you're making the part with. It happens to be ABS in our machine, and then the ABS comes in the form of a filament on a spool, and the support structure is done exactly the same way. It is it's a filament that is wrapped around a spool inside a cartridge that's kind of inserted into the machine. The filament, I believe, is sugar-based, and it's heated to a particular temperature, and then it solidifies, and then once the part comes out, it has both the plastic and the support structure, and we chip the support structure away by hand, and then we place it in a water bath that's heated, and the support structure then kind of melts away, and then we take the part out, wash it, and dry it.
Great, thank you. Okay, I have a question for Ben. Do you see variation in the through thickness microstructure in metallic parts?
I haven't actually looked at that as of yet. These parts really are not highly stressed, so the actual material properties weren't really much of a concern for me. I can imagine, though, that you would want to take a look at that if you were going to be using highly stressed parts.
Right. Okay, thanks.
Mm-hmm.
Okay, so I have a question that I think would apply to both Ben and Brad. The question is, regarding additive manufacturing for prototyping fuel cell components, are you aware of anyone prototyping composite or metal fuel cell separator plates?
Am I aware of anyone actually doing that?
Yes.
I would have to say that I am, but I'm not really at liberty to really discuss it, I guess, without, IP in place.
Gotcha. Okay, I will go ahead and take, I'm getting a couple general questions on the DOE side. I'll go ahead and say that, try to answer a few here. Someone asked how small and medium enterprises can have access to things like the MDF, which tend to work with a lot of larger industry groups. I'll just say that there are methods in place, and we are certainly working as hard as possible to make sure that small and medium manufacturers do have access to the facility. And there's a set of activities called technology collaboration projects, and that would be the method by which we would try to get the smaller manufacturers in the door. And we do have several manufacturer partners at this point. So please just continue to reach out to me or the MDF if you have any interest in participating in these programs. I would also, there's some questions on, is DOE focusing on any process controls for additive manufacturing process? And the answer there, again, is yes. We have a few R&D projects that are actually working on the development of in situ process monitoring and process controls for particular processes. Okay, so it's about 12:59. So I guess I don't think we're going to have a chance to get through all these questions, but thanks everyone for your time and for putting in these thoughtful questions. Definitely want to again thank Brad Wright and Ben Lunt for your time here today. I think your presentations were really really helpful and informative. So thanks everyone for your time. Amit, are there any closing remarks?
Yes, thanks, Blake. I just wanted to thank everyone for coming, and especially thank today's presenters, Brad and Ben. Sorry, everyone, for the technical difficulties we had midway through the presentation. Now, the slides and a recording of the webinar will be posted to our website within 10 business days, and we will be sending an email to participants when it is posted. So, thank you, everyone.
Thanks, everyone.